So yeah, Luca, I think is a 5th year. Is that right? Starting your 5th, and we're actually not finishing your 5th because you're going to defend this fall. And he works for Paulo down below, and so right off the bat, you know 2 things about him. He's quite a bright fellow, and he's also quite nice. I know Paulo has said before in public to new graduate students, if you want to work for me, it's going to be very difficult. I'm hard to work with, I'm hard to get along with, and I expect great things. And so take that into consideration before you think about coming to visit me. And it's almost, you know, exactly what he said. So Luca comes with high regard in that respect. From here, he'll probably, he's mentioned, probably go into finance after his dark matter search. So, that's what I'm interested in. Anyway, take it away, Luca.
Thanks for the kind introduction. Hi. Today, I'm going to present you my work with Paolo, Professor Paolo, during these 2 years on the dark matter. Specifically, we focused on axion called dark matter. So, let's see. As you know, this is the content of the universe today. And sorry for the figure, I thought it would focus. That's what comes out. So, we had, this is a pie that represents what recent measurements show about, tell us about the content of our universe today. This tiny 4% is atoms, or as cosmologists call baryons, meaning not just the standard model baryons, but basically all of the standard model particles that are non-relativistic today. So this is the fraction of stuff that we know exists, while the other 96% is stuff that we know that should exist, but we don't know its true nature yet. It's not stuff that is embedded within the standard model or in a greater picture. It's not within the frame of a solid stabilized theory. This 4.23.7% of the pie represents what the non-relativistic stuff that hangs around in the universe, and of which 85% of this pie is cold dark matter. So it's what's known in the universe to actually guide and rule the dynamics of galaxies and stars at these scales. And the rest is in the form of dark energy, which I will just mention here. I won't talk about it right now. Although we are working now on axion-like papers, and they're, sorry if I talk too much, and their role as a okay, good. So yeah, I won't talk anymore about dark energy in this talk. I'll just focus on what the cold dark matter is. There are various possibilities. One of them is the axion. I like to present a timeline to see where we are. So the axion is a particle that was originally, it's a pseudoscalar, first of all. So it takes a minus sign when you apply a parity transformation. So you reverse x to minus x. It's a pseudoscalar particle that appears first in 1977. So by this year, Che proposed a solution to the so-called strong CP problem that appears in QCD theories. What is this problem? So within the sector of QCD in the standard model, theoretically we expect the CP symmetry not to be conserved, to be broken at some scale, because of the presence of some terms in the Lagrange that allow violation of the CP. But in practice, this is not observed experimentally. So there must be some explanation to why the CP symmetry is conserved, it is preserved within the QCD sector of the standard model.
So, sorry, the CP is charge parity.
Charge parity. So there are three main symmetries that you can apply to a field theory. One is T, time inversal, to switch the time frame. P is parity, you switch to spatial x with minus x. And G is charge conjugation, you change the sign of the charges of all of the charge particles in your theory. CP is violated to some degree by the weak interaction only. And that is shown experimentally. But in theory, you could have some degree of CP violation by the QCD sector also. You don't observe such a violation. So there must be some mechanism that we don't know yet that comes around in the within the QCD sector that prevents CP to be violated. And the, let's say, queen mechanism is actually the most viable up to now.
But does QCD predict the energy scale at which it should break? I always thought that the energy was right, so maybe it's at high experimentally unattainable energy.
Mm-hmm. Yeah, that is what's expected with the axion itself. We'll go through that. That is actually the focus of this talk. So, in 1977, this new symmetry is a human symmetry that preserves the CP symmetry was introduced, and just 1 year later, two huge physicists independently computed the axion mass in terms of a parameter Fa, which is an energy scale, which will show it's a really large scale. It can go up to the Planck scale. Okay, so in 1983, other people independently showed that the axion can serve as a cold dark matter. So this is a different problem. You have a particle that is introduced within some theory to solve some type of problem. For example, the axion. Or for example, supersymmetry. Solve some problem internal to the standard model itself. But this extra pieces of Lagrange that you introduce in the theory also give you some good candidates for cold dark matter. This is what is meant to be by a good cold dark matter candidate. Some candidate that serves for something else and provides cold dark matter, like the neutralino or the axion itself. That's why the axion is a good cold dark matter candidate. And this was shown in 1980, so almost 30 years. Axions as the cold dark matter particle during inflation was actually studied in 1987 by Linde. This means that the axion is the cold dark matter particle, it's not the inflaton, but it's present within inflation. And this kind of axion has totally different properties from this one. We will see it in depth. And finally, in 2002, a successfully supersymmetric axion model was built after a decade of attempt. Okay, so this is the mass of the axion to get familiar with the particle. I thought the axion mass, which is temperature dependent. What does it mean? So the higher the temperature scales, the smaller the axion mass is. So on these scales, we have the axion mass as a function of temperature, with respect to its mass at 0 temperature. So this ratio has to go to 1 at smaller temperatures. And here the temperature scales with the lambda QCD, which is a parameter within the theory itself. And I take the scale to be 200 MeV, so 0.2 GeV.
What does temperature mean for a particle?
It's the temperature of it's the temperature of the surrounding plasma. Because especially in cosmology, all of these particles are within an ensemble of quark-gluon plasma.
So its surroundings determine its mass.
It's surrounding all of the other standard model and possible exotic particles that hang around in this plasma. Back in the early universe. So, as for the early universe, you know that time and temperature are strictly correlated, so that the earlier I go, the earlier I see, the higher the temperature is. So, to that regard, time runs in this direction, and the Big Bang is around here, and then the universe cools down to the present temperature. And so what happens to the axion mass? Sorry again.
You can turn that off in the settings really quick if you start to
I would love to.
system settings.
There's also a program called caffeine.
Yeah.
Yeah. Then display again. Yes, screensaver.
Energy saver.
Energy saver. So you just go here. Okay.
And then you're on your batteries, so just change those to like that.
Yeah.
Slide them over. So the 2 bars, slide them all the way to the end, the far right.
Okay. Thanks. And that's it.
Yeah.
Perfect. More interruption. Sorry for that. Okay. I was saying that this is the axion mass. So as the universe cools down from the Big Bang, its mass rises. So it has initially a negligible 0 mass, and then it rises to its present-day mass. Yes.
Yeah, can you comment like what is the physical significance of when it reaches that plateau?
So people are able to compute the axion mass in these 2 different frames. So when the temperature is much lower than lambda QCD, and when it's much higher. Here in between, there should be some smoothing out, which people is not able to evaluate analytically. So I decided just to plug it like that here. But here is where the lambda QCD, where the temperature is of the order of lambda QCD, and this computation here breaks down. So the axion mass at 0 temperature is computed because this hypothetical particle has the same quantum numbers as the pion and the eta meson, and so it mixes up with them and acquires a mass that you can compute, and is the axion mass at 0 temperature. The temperature dependence, which you don't see because of this. I should press close.
Maybe just click on the slide.
This temperature dependent, so the axion mass turning off with t to the -4, comes from fancy QCD effects that are called non-perturbative effects that actually screen the axion mass and make it to be temperature dependent in this way. So it's around 2% of the mass at 0 temperature times t over lambda to the -4. Okay, so my main question is, where in the parameter space is the axion 100% of the cold dark matter. So I assume that the axion exists, and it also serves as the cold dark matter particle. We will see that because of that, we're able to find a value for the scale Fa that appear in the axion mass, and so fix the mass of the axion itself. So we study this parameter space with this additional constraint, that the omega is the energy density for a particle in terms of the critical density. Critical density is a quantity related that is introduced in cosmology and tells you when the universe closes down. So it's a rho c is a borderline, a watershed between an open universe and a closed one. So a universe that always expands or recollapses forever. Okay. So omega is this ratio here. Omega for some quantity. Omega alpha. And h is the Hubble parameter today in units of 100 kilometers per second per parsec. So it's basically h is the rate at which the universe is expanding today, is in some units. It is of the order of 0.7. This is the measurement for the cold dark matter today. So omega on its own, if you divide by h squared, is around 23%, which is the number we solved before the pi. So we fix omega computed to the measured number of cold dark matter observed. And what we've done in our papers is updating the constraints, and the value of the axion density is better computed than before, and we have included harmonicity in the axial potential. We'll see what that is in a second. This is the parameter space we're dealing with. We have this Fa, this symmetry breaking scale, which is the energy scale at which the Pacheco symmetry breaks down. So you have this sombrero at the potential, and the axion is the angular variable in this potential. I assume you're familiar with this type of potential that appears in Landau and Ginsburg theories, or in Higgs particle physics. So N is and D are technicalities. One is called the Pacheco color anomaly, and the other is number of degenerate CQD should be QCD, QCD vacua. So it's basically the number of vacua that there are within this 0 to pi angle. These two acronyms come from 8 different people actually, two sets of 4 different people who studied 2 different types of axion, which differently couple to quarks, leptons, and photons. So these 2 models have different couplings to standard model particles. We'll pick one of them, EFSD. So we have our coupling to the standard model fixed. HI, the expansion rate at the end of inflation. So when inflation ends, the expansion rate of the universe is HI. Theta I is also a parameter in the space. It's called the initial value of the misalignment angle. So the axion field, you can say it's A of X, pseudo-scalar field. Theta is an angle, which is the angle in this Landau Mexican hat potential, and is defined as A over F. So when this U1 symmetry breaks down, the axion field in the early universe. The axion field will have a specific value of this misalignment angle, a specific initial value of its field, which we call theta I. And then the dynamics of the axion is such that this theta relaxes toward 0 values, and which means the CP problem is solved, because we want this theta to be 0 in order to have this problem solved. And then we have axionic strings, also which are topological defects I'm going to talk about. And these are, again, acronyms of people who work on that, and there are 2 models for that. So we assume that n is equal to a t is equal to 1, so we have just one vacuum. And we pick 2 different models, axionic models, so we are left with just 3 parameters with 1 constraint. So the axion is 100% constant. And the 3 parameters we're dealing with are the initial value of the misalignment angle, which is unknown. We don't know what the value of the field is when the symmetry breaks down. The energy scale, or if you want, you can trade it with the mass of the particle itself. And also HI, which you can think of as the amount of gravitational waves, is related to that, observed today, is related to this parameter. Okay, so how are axions produced? I don't know if you saw my abstract, in which I quoted a value of the mass of the order of 100 microelectron volts. So extremely tiny particle, extremely tiny in mass particle. Extremely light, so if you produce it thermally out of a plasma, you would have a particle that is extremely ultra-relativistic. Because you have basically a massless particle coming out of a plasma, and you expect it to be ultra-relativistic even today. So it cannot serve as the cold dark matter. Cold dark matter, I remind you that cold stands for non-relativistic. So how come such a tiny particle is non-relativistic today and has been relativistic throughout its own history, expansion history? Because the axion is produced no thermally. It's not produced by relaxation out of a primordial plasma. Instead, you pick. Instead, what you do is following its dynamic and pick the 0 mode, the mode that has 0 momentum, and that serves as a Bose-Einstein condensate. That actually makes up the cold-dark matter today. So let's start from scratch. We have an initial misalignment angle, theta I, which is basically the value of the axion field when this new symmetry breaks down. And as we've seen, the axion mass is 0 to begin with. So this value of the misalignment angle is frozen until the universe cools down at a temperature of the order of the GD, and is specifically given by this equation here, in which on the right-hand side we have the temperature-dependent axion mass, which we've seen before, and on the left-hand side, sorry, we have the Hubble expansion rate, which is how fast the universe grid is moving, actually expanding. So you know you can pinpoint points within the universe, and even if they don't move between themselves, they have 0 peculiar velocity. The grid itself is expanding, and so they actually tear apart. This is what happens to galaxies. You have an intrinsic speed, precession speed, that is due to the expansion of the universe. And h is actually the rate at which this grid is expanding. It depends on the content of the universe, on what is the dominant matter the content, the dominant content of the universe today.
Does it also depend on dark energy?
Yeah, today is depending on that dark energy. It's 75%. So that is the dominant contribution. Today we are at this particular time in which we have 75% is lambda, so it's vacuum energy, and 25% is a cold dark matter. So they're both important. But we are transitioning from matter domination to this lambda domination. So eventually, yeah, it will be lambda, unless other forms of energy that we don't know. But in the past, it was radiation, because we had a hot plasma. So what now is the cold dark matter was actually relativistic at the time, and the standard model particles were relativistic, and they were dominating the universe. So H is actually, at this time, which is of the order of the GeV, H is peculiar to radiation dominating the universe. What we've done in another paper that I'll show you, which I'll show you the result, is changing this H from standard cosmology, radiation dominated cosmology, to non-standard cosmology. So you can think of other fancy non-standard cosmologies that are plausible, because no one can disprove that. That's what we did. So, and T1 is the temperature that comes out of this equation here. Knowing T1, we know the density of particles. So this can look contrived at first, what that actually means. So for a scalar field, you know that the energy density is given by 1/2 the mass square times the value of the field itself squared. So for an axion, phi is written, is A, so it's written as theta times F, which appears here, Fa squared, theta squared. Na is the density, which for a non-relativistic particle is just the mass times the number density. So that's why you have just one value of the mass and not two, because I'm talking about the number density, not the energy density. What else? Chi is a correction factor. Comes out of this. This equation is not 100% correct, so you have to introduce some correction factor in the temperature. And this F of theta I that appears here is a harmonicity correction. That comes out because the axion potential is actually not exactly a pure quadratic one. So in the equation of motion, this term is not exactly linear, it's not theta. When this value, theta I, is of the order of pi, you can appreciate these unharmonicities. You cannot Taylor expand this sign of theta this way. So you have to include this unharmonicity function to get the correct result. And this enhances the correct energy density of axion by 1.4. Might still be important for computing that. So I know the number density to begin with. So now, and axions are then produced. So if I fix my volume of universe, I know the number of axions within that volume. I follow the evolution of that volume to the present time, so I can compute what the number density and thus the energy density is today. That's what is done by this consideration of computing axion number density, and gives me the energy density today to the critical energy density ratio. Okay. So there are also strings that can give you some cold dark matter axion component. What is string? So imagine that when you have your check-in symmetry, your U1 symmetry breaking. In different patches of the universe, the initial value of theta I can have different values. So we can have a patch of the universe in which the value of the theta I is phi, another patch which is phi prime. So there are bubbles in the universe that have different values of this initial misalignment angle. And between them there is a tension. So we have actually a potential wall between these two bubbles. And we have strings connecting these walls, which are other topological defects. Eventually, all of these defects have to decay and give a hot component and also a cold component of axions. All of this seems kind of contrived by itself, but people have studied simulations of axionic strings. They came up with the fact that the energy density in strings is actually proportional to the energy density in the misalignment, from the misalignment effect, which I just showed. By some ratio that depends on the model, but I am fixing the model, so I'm fixing these parameters. So I fix these parameters here. I know what the energy density from the misalignment mechanism is, because I just showed you one slide ago. So I know what the energy density from strings is, and I can include them in the model itself. When you switch to non-standard cosmology, you have to do some little more work, because these parameters here depend on the model itself of the cosmology. This beta, in fact, is beta here. This is the scale factor that goes as t to the power of beta. Beta is 1/2 for radiation-dominated cosmology, but it can be a generic beta in different cosmology, what's called non-standard cosmologies. So we computed these values here for generic cosmology. And you see, when beta is close to 1/3, this value can be pretty close, pretty huge. In fact, we find that in some cosmology, this contribution is 100 more or less the contribution of this line. Okay, so now we have all the tools to show results. So what we've done here, finally, this is the standard cosmology. This is the evolution of our universe, in which we have, well, this is the famous Friedman equation that I didn't put it before, but I talked about it. This gives h, the Hubble expansion rate of my grid, as a function of rho, which is the energy density, the content of the universe. And rho scales differently with the scale factor for different content. It's constant for inflation and vacuum energy. For matter, it scales, rho scales with the volume. For radiation, you have an additional A that takes into account the redshift itself. So, yeah.
Sorry, but do we know that vacuum, that it scales linearly here? But that vacuum energy is always constant in the universe?
This lambda?
Yeah.
Yeah. You can write. So, yeah, this is the dominant. You can put all of them together in this equation, and you can see that the ratio of each of them is marked at specific locations.
So when you say vacuum energy, does this relate to dark energy?
Mm-hmm.
Okay. Am I mistaken? I may have heard in the past that dark energy parameter may have changed over the history.
Well, that's a possibility. So
here
there are different models. There are models in which it's constant, models in which it's slightly changed. But even if it's constant, if you go back in the past, in which the universe was smaller, there was less energy density. No, there was the same energy density, but there was less energy because there was less volume. But the matter was dominating.
Based on the graph here, can you scientifically predict when or if the universe is going to hit maximum entropy?
Well, maximum entropy, not based on this graph, entropy is not here. And it depends on the model itself for the dark energy, I think. I don't think there are troubles if it's a constant. There might be troubles in other. No, this graph is just h, or it's logged as a function of this scale factor, which you can train for the time. So you have very early time, and then the universe cools down to the present time, which is here. That's all you can see from here. You see that the universe decelerates. That's all you see, and there are different slopes that belong to different contents of the universe.
So when you're describing the different patches of different theta i's,
Yeah.
now, like, do those still exist in the universe today?
No,
Or do we imagine
no.
it's dominated
Otherwise,
by-
they would dominate the universe. So they must have gone somehow, in some ways. So one way is inflation, because and this will be a landmark. It will be very different if the axion is present during inflation or after inflation. So if it's present during inflation, then all of these fancy topological defects are washed out. Are washed away.
Is there some, would the axion interact with an inflaton? If with an inflaton, if during inflation, if you had axions during inflation, is there some sort of coupling to the inflation field?
So unless the axion is the inflaton itself, which can be.
Yeah. Okay.
Yeah. No. That wouldn't be a minimal model. So I stick to minimal models.
Okay. And how do you determine, I guess, what theta I to choose today? Or is there?
Yeah. So in the case in which the axion decay, the Pachachin symmetry breaks after inflation, what you have to do is basically take an average, because within a Hubble horizon, you assume that all of the different theta I are reached with some probability. And so you just take the average of all of them, which is plausible.
Yeah.
Okay, so axions in standard cosmology is produced here during the radiation-dominated period. So here is where we have 1 GeV around. And results finally are shown here. So this is the parameter space as a function of h sub I, the Hubble expansion rate at the end of inflation, versus Fa, this energy scales in GeV. So you see that this energy scale is quite large, and it has to be quite large from measurements. So it's bound to some few 10 to the 8 GeV from the white dwarf time. So there are these stars that would turn into white dwarf too fast if action were coupling too strong to standard model particles. So this sets a lower bound on Fa. On the contrary, Hi, I told you, is related to the amount of gravitational waves, which we don't see yet, but we expect them from inflationary models. And so this sets an upper bound on Hi here, which will be removed here by Planck. Okay. Other bounds are here. This is a direct search of axions that excludes this range of Fa and will be moved down hopefully in the future. But this is just projects now, especially this one. It's very ambitious. So, as I told you, this is a landmark. There's a watershed between the axiom, the Pachachin symmetry, and the axiom being present during inflation, here at this left side, or after inflation here. In fact, here you have also the theta I parameter to answer better your question. And here you don't, because here you average out. So you take an average of theta I, and that parameter disappears, but not here. Okay, so I'll start talking about this portion before, which is the historically most relevant, historically. So, check with integration after the end of inflation. So, we have an average theta I over a Hubble volume, because all of the possible theta I are reached. And harmonicities are important. Sorry? This is the, yeah.
What is the Hubble volume?
The Hubble volume, well, you can take, so the Hubble parameter, H0, has units, it's a rate, so its units are 1 over time. So H0 to the minus 1 has units of time or length. So H0 to the minus 3 has units of volume. So roughly, this gives you the volume of the universe, of the visible universe, roughly. And this is just for H0 today, but you can take a H at whatever time, and that's the size of the universe, the volume of the universe at that time. So people refer to H to the minus 1 as the size of, as the length size of the universe at that time. So this is the harmonicity function that I used, and this basically is an analytic function that interpolates between two numerical results. I took an analytic function because it's easier and we don't know what the exact function is. So there is a function that interpolates between the two while not using it. And the string decay contribution is 0.8 of the vacuum realignment. So both two non-thermal production models are give the fairly same amount. And this is this patch here. And this is the thin line that I find for the value of FA. I'll tell you later what that is. So this is the other possibility in which the axion is present during inflation. This is a constraint by non-adiabatic fluctuations. It means the instruments today, specifically WMAP, is able to constrain the non-adiabatic fluctuations, or a fluctuation in the axion field with respect to other components, photons, in the plasma. And it gives this line. Basically, it tells you the axion is not 100% here. It can only be in this patch here. What are these other lines? So these other lines are levels of this function here. The theta I and FA, these two parameters are linked in this region by a specific function, which is given here. So you have to sit on this function and have this, for a certain FA, you have to have a specific value of theta to have the axion as the product matter. As you can see here, for a specific FA, you have a specific value of theta. If you sit below, the axion mass is underabundant. Otherwise, it's overabundant. You have more axion than what the contact matter will observe. So this is actually an excluded region. This region is still allowed, but the axion is not the contact matter. You have to sit here to have 100, on this line to have the 100% of the contact matter. Here, this is interesting. You have, again, a strong CP problem. What does it mean? It means you have a functioning problem if your energy scales is too high, lies above the gut scale, of the order of the Planck scale, because your value of the theta I parameter is too low. So you have to fine-tune theta I to have the value of FA. It's a fine-tune problem. You might like it, might not like Okay, finally, this is the axion mass we find. It's different from the abstract because I updated that to by including a different model for strings, which is more reliable than the one I used 2 years ago, and I updated the uncertainties by including uncertainties in the quarks also there. So a tiny axion mass, and this is a value of Fa of the order of 10 to the 11 GeV that we expect. Future will tell if this is true. I have 10 minutes less to run through non-standard cosmologies, so I'll try to be. So this is the standard picture I showed you before. What happens for non-standard cosmologies? So from Big Bang nucleosynthesis on, so going backward towards towards Big Bang, we don't have any data, so we don't have any particles that tells us, well, the universe was radiation dominated here, was whatever dominated. We don't know what the history of the universe here is for temperature that are above 1 MeV. And the axion, as I told you, starts oscillating at 1 GeV. So this is a big black box in which I can put whatever non-standard cosmology I want, because actually there is no data. So anything is possible. One non-standard cosmology. So for standard cosmology, one just assume there is inflation because of a particle that I need, and then the universe kicks into the radiation-dominated one, and then it cools down. But what happens if I have a low temperature reheating cosmology? What is this? So we have inflation, and instead of going abruptly to radiation-dominated one, we have a smooth transition in which the inflaton, or a residue from inflation, dominates the universe. It's a massive particle that dominates the universe and slowly decays and releases entropy and reheats the universe. So instead of having an abrupt release of entropy, as in standard cosmology, we have a slow release of entropy and of particles. So this is a non-standard cosmology, but it's still a plausible cosmology because there are various models that predict this kind of behavior. It's rather natural. You don't, after inflation, there is something, some residue, have some decay time, so that this happens. And notice the behavior of H is the same as a matter dominated, because you have actually a massive scalar field dominated in this region. In this case, this is what we find. So, theory heating is a new parameter here, and marks the temperature at which the universe transitions from this decaying field domination to radiation field domination. This one here. Here is where theory heating is. There are different curves for different theory heating. This is again the watershed. We see that with theory heating lowering, the value of the axion mass lowers as well. This is what we found, and this is shown here, until you reach the point at which you have a phase standard. Okay, and this is on the other side, when the axion field is present during inflation, you have different curves in which you want your axion particle to be the cold dark matter for different values of theory heating. So this is the same curve as before, but just it moves with this particle. Okay, so I have another non-standard cosmology. I'll skip it. Just and I switch to conclusions. So this particle, the axion, which is a more motivated theoretical particle existing, can also be the cold dark matter. Where? In the parameter space. So if the projectile symmetry breaks after inflation ends, so we average over the values of the theta I, the axion mass is this value here, so order of 100 microelectron-volt in the standard cosmology. In the low temperature heating cosmology, it might have a much smaller value. We haven't seen the declination, it's much larger. If the projectile symmetry breaks actually during inflation, and the axion mass is present during inflation, you have your parameter space, which is constrained by these non-aballaticities observed. And you have a larger parameter space in low temperature heating cosmology. So, thanks.
So you said that the mass was dependent on the temperature. Is that
On the cosmology itself.
is that because you assume that?
Oh wait. In general, the axion mass or the axion here in this cosmology?
I don't know.
You're talking about this?
Yes.
This is in general. Yeah.
Okay.
Okay.
Okay. So for
This
that,
is true even if the axion is not the cold dark matter.
is that because the particle is in thermal equilibrium with the plasma? I just don't understand how the surroundings can determine the mass of a particle.
I think there's people who tells you better about this. So, no, it's due to, it's called, I don't want to hide behind technicalities, but it's called instanton. It's a solution to just a pure gluon field. And basically, you have, as computed by that in that paper, this instanton screens out the axion mass, or whatever pseudo-particle scalar mass. And depending on temperature, you have instantons that have different sizes. And so the screening is different. And that's why it gets this temperature dependence. Is this correct? More or less. Yeah.
How can you screen maps? Is that
Because this particle acquires a mass from its surrounding. Just yeah.
So, is it, or what is, should I think of it as a quasi-particle, as some sort of oscillation of the plasma, or is it an actual?
No, it's an actual
particle.
I mean, there is an actual field that comes out of the addition of a piece of Lagrange. There is a field, and the particle. Yeah.
The zero temperature you have marked, is that absolute zero, or how are you measuring?
Oh, yeah. It would be at absolute zero, but today we just take it to be absolute zero.
All right.
Approximately.
So, so you had said that there has to be something which, in order for it not to break CP violation, because we can imagine if you break CP violation. So, I'm sorry, I didn't quite understand. So, it is like in that, so it's like in that field itself, like when you talk about a certain cosmology, that is what's causing it to not break that CP violation, right?
Oh, you mean here?
Like, yeah, so why is it not?
Here. Where I said strong CP problem again? No. Here? No.
Yeah, okay, I'm sorry, yeah, so why is it not breaking the CP violation? Because we predicted that it would, right? So
It will. You don't want CP violation.
Right, so what, yeah, you had just said that there's something so that it doesn't break it, so I'm not really sure
Okay.
why it's not breaking it.
Okay, so let's see. The axiom comes from this fact. You have this Lagrangian, which you have this theta,
Oh.
the Bloom field, and here you have a 32 pi. And this breaks CP because this is a pseudo. Is a
Oh, because it's term one and term two.
well, this is just a term. It doesn't preserve parity in the QCD theory. In short, what is done with the axion is promote this parameter to be a field, and then you have dynamics. And the dynamics of the field is that this theta sits at the bottom of its potential, so it gets a zero expectation value, and this whole term cancels. You still have the rest of the dynamics of this parameter here, but this term that violates CP cancels. This is the important thing. And this is how you cure this strong CP problem with the axiom. In short.
Luca, can you back up a few slides to your first big yellow graph?
Yeah.
Yeah, so your double line there.
That would be
it's
at
just below
this one.
Yes, it's just below the expected sensitivity of the Carrick experiment. Do you expect it to be experimentally resolvable?
Yeah. So as you've seen, it's very hard because sensitivity haven't reached yet this region. This is so I'm optimistic this will be done as an experiment. I haven't heard much about this. You know, I've showed you other possibilities, like in other cosmology, the axion mask here. So we don't really know where it is. Look at here, it can be anywhere here, except for this already excluded region. So people, this is just an indication of where it could be. Or it's an indication. People used to not to include strings, not to include anharmonicities, coming up with a much higher value of the axion mass. So if they were to look for an axion mass there, not finding it, well, that doesn't mean the axion doesn't exist, because you don't really know where it is. There are too many uncertainties. There are orders of magnitudes to be expanded. So I don't know about this particular value here, but
So you're not married to that. Okay. The other thing I want to know is how you base your whole model on only a single vacuum. How can you do that?
Well, yeah, that was a specific.
Actually, what I want to know is how can
Yeah.
you have more than one vacuum?
Now there was or how can you have more than one vacuum?
Yeah.
So one vacuum only. So you mean n equal 1?
Yes.
One vacuum only was specific of the axionic model I used. This acronym here.
Yeah.
These models also predict n equal 1. So it's not that I choose.
But what does it mean to have?
More than one. Yeah. So so let's see. The axion moves in this. There are basically two potential in which it moves. What is this Mexican hat potential? This. No. But with once below this energy, the energy at which this symmetry is broken, the axion sits here and is just an angular parameter. But you still have another potential that is a cosine. So and each one of these is a potential vacuum. So this is due to temperature, the same temperature effects that give the axion a mass. Basically what they do is tilting this Mexican hat potential so that there is a preferable vacuum. How many of them? Just one if you just tilt it. If you also deform it somehow, there are more.
So how is deformation usually?
There is this residual potential.
I assume there's an additional potential to create
Yeah,
some slant to the system.
Yeah, you have just a circle that is tilted.
What's the tilting potential?
The tilting potential comes from this non-perturbative effects. That also give the axion a mass. Actually, this axion mass is computed from, it's the same stuff, it's computed from this effective potential. It's written as MA squared T FA, must have this, and times 1 minus cosine of theta, or theta over m. So you just recognize this piece as the axion mass. You just compute one thing, the potential, which is tilted. And then you recognize this as the axion mass. You give it the name, and it's the axion.
Anybody else? No? Okay. Thanks, Luca.
Yeah.